Hi there. The purpose of this video is to prove by experiment what the resistivity of copper wiring is. So resistance of a cable is the resistivity value times the length of the cable divided by the cross-sectional area. So the resistivity P, which is material dependent, equals the cross-sectional area times the resistance measurement on the cable, which we will do on a 100-metre drum, divided by the length. The cross-sectional area is going to be 1.5 because we're using 1.5 mil twin and earth cable and also 1.5 single core earth cable. And we want to prove by experiment that the measured value of resistivity matches within reason the theory. So if you look up a book, the theory for copper is 0.0178 microohm meters. That's for annealed copper. Annealed copper is used for copper wiring because it's flexible, malleable and conductive. It doesn't need to have particularly high tensile stress like copper piping. So it goes through an anneal process where it's heated up and then cooled down, so it gains flexibility and malleability. It's what you need for cables so that you can bend them to a reasonable extent. So what we've got here is a setup. We'll move that just now. What we've got at the moment, we've got a meter there which has been calibrated. What we're going to do, the cables, you can see there the 0 ohm value for the connectors shorted together. So what we're going to do is put it onto the neutral wire, 100-metre drum, both ends, and see what it measures. So it's measuring there 1.22 ohms. We'll remember that. We'll then put it onto single core earth cable, 1.5 mil square cross-sectional area. We're reading 1.20 ohms. So let's repeat the calculation, let's repeat the measurement and see if it's not just random chance. Let's see, we're repeating it again, 1.21. So that gives us confidence. We'll take 1.21 as the measured value and then we'll do the calculation. Just out of interest, if we use the same connectors and switch that off, let's just see what a relatively cheap multimeter will do in terms of measuring that particular resistance, which was 1.21. Let's see with this, let's see what it measures as 0. We zero it. It's coming down to about let's see, 0.2, 0.3. Okay, so let's subtract 0.2 and let's measure it and see if we get consistency of results. What we've got there, it's measuring, it's going to settle down, it's measuring 1.5. If we subtract 0.2 from that, we get 1.3, which does match up with the calibrated meter. Let's change to another type of multimeter. Let's go for a Fluke 115. Again, the same connector, so we get consistency of that. Let's zero. Let's see what it reads when we zero it. What's happened there? We want to be able to, we're getting 0 ohms there, so it's reading, there we've got 0.1, we'll subtract 0.1 from the reading, and let's see what we do onto there. We're repeating that, so there we've got 1.3, if we subtract 0.1 we get 1.2, which matches up with the calibrated mega reading. Let's just double check onto the cable drum. Again, we're repeating experiments. Experiments should be able to be repeated. Again, we're getting 1.2, 1.3. Let's take 1.2 as the reading. So take that off. So if we put in our 1.2 as the measured value, 1.2 ohms, and we do the calculation. So we have 1.5 times 1.2 ohms divided by 100, and it comes out to be 0.018. So we put that up there. So what we're getting by experiment is the theory 0.0178, which is, we'll round it off to 0.018, and by experiment our calculated value of resistivity from our 1.2 ohm 100 metre drum is 0.018, which matches up with the theory calculations, and it also matches, if you look at the BS 7671 wiring guide, on-site guide, on table I1, it says 1.5 should give you 12.1 milliohms per metre. If you do the reverse calculation, that comes out to be 0.018 micro ohm meters. So we've proved the theory resistivity for annealed copper against experiment, and it comes out to be the same value. Thank you for watching.